Now the next thing that we are looking at is made, which is masked, okay? Sure. So what you're saying is that I have assumed a certain ordering of the random variables, but that ordering can be different. So it is up to you, right? So what you're saying is that I'm assuming that xk depends on everything from I to k minus 1. You want it to depend on a neighborhood, right? Both of these are assumptions. Do you agree with that? And the first, whatever I have assumed, right? I have assumed a certain ordering of the random variables. You could assume a different kind of ordering so that this factor becomes one of the factors in the distribution. Does that make sense? It's not trivial, but you could do that. Okay. And also, I mean, I know when we're doing convolutional neural networks, we argued that it only depends on the neighborhood and so on. But we have also seen other cases where it could depend on something at the top, something at the bottom, and so on. So this is a modeling choice which you are making. Once you make that choice, these questions are not really, do not really exist, right? I mean, you have made a choice that is going to depend on all the previous pixels. If that's a choice, you can use this. If you're not happy with that choice, you'll have to do something different. No, so then you have to talk in terms of whether the KL divergence between the true and the approximate is similar or something like that. Yes, it's again an approximation. Just as variational inference is an approximation, just as Gibbs sampling is an approximation, this is also an approximation. Yeah, so you're looking for some theoretical guarantees on the true distribution versus this. I am not aware of those. I don't think the original paper also has that, but you can go and check. But I don't think there's such a guarantee given on that. So this is masked autoencoder density estimator. Density estimator is always fine with us. Now, given that autoencoder appears in the name, we're going to start with an autoencoder and then try to come up with a density estimator by modifying it, okay? So suppose the input is again n dimensional, then what's the output of an autoencoder? What's the dimension of the output? N, right? So input is n, output is n. Now coincidentally, how many factors do we have in the explicit factorization or the chain rule? N, right? So the question that I'm going to ask you now is that, can we somehow tweak the autoencoder so that instead of reconstructing the input using its n output units, it can instead predict these n probability distributions that I'm interested in. Is that fine? Okay. So that's the question that we are asking. Can we take a regular autoencoder, tweak it in a certain way so that instead of predicting or reconstructing the input, it predicts these n factors from our joint probability distribution. Okay. So what are these outputs going to be? In that case, this is going to be P of x1, P of x2 given x1, P of x3 given x2 comma x1, and so on, right? Now, why is it not straightforward to do this with a regular autoencoder? Because it is fully connected. So if it's fully connected, every output unit sees every input unit, and that's not fine, that's cheating, because you're trying to predict x3 and you're already seeing x3 as well as everything that follows it also, right? So we'll have to do something to make sure this autoencoder is not fully connected, and we have to make sure that when I'm looking at x3, there is no path to x3 from x3, x4 onwards up to xn. There can be only paths to x3 from x1 and x2. Does that make sense? Very same to what we had done in the NAID architecture. Is that okay? The same idea. And so what we're going to do is that we're going to use masking again, which means that we're going to mask out some connections so that our output, every node in the output, is only connected to the relevant inputs. And what are the relevant inputs? The ones which appear on the given side. So it's x3 given x1, x2. So x3 should only see x1 and x2. Does that make sense? Everyone? Okay. So what we'll do is we'll start by assuming some ordering on the input. So we'll assume that the inputs are ordered 1 to n. Okay, so in the case of image, this is straightforward. You can just go from left to right and then top to bottom, and that's your ordering. Okay, so I'm going to number these pixels 1 to 4, 1 to n. And of course, the outputs are also numbered 1 to n because it's x1, probability of x2, probability of x3, and so on. Okay, does this numbering make sense? Now what I'm going to do is I'm going to assign random numbers between 1 and n minus 1 to every node in the hidden layer. Okay, what does that mean? What will I do with this numbering? Can you take a guess? What would I want with the node number 2? It should only look at those inputs which are less than or equal to 2. Okay, why? What will then happen if I connect this path? Okay, so now let's see. If I have the output node 2, what would I want the numbering of all the nodes which appear on the path from this output node to the input nodes? Less than or equal to 2. No, sorry, actually less than 2, right? So does that make sense? So that's where we are headed. Right? We are going to number these nodes, make sure that the number on the node defines how many inputs it's going to connect it to, or rather which are the inputs that it is seeing. And from there we can connect a path from the output to the input such that the given output sees only the relevant inputs. Is the overall idea clear to you? Okay, so let's look at it. So let's, for the input layer, the interpretation is very clear that if I have a node number 2, then it's only going to look at inputs which are less than equal to 2. Okay, that means it's only going to be connected to 1 and 2. And if I have a node number 3, then it's going to be connected to 1, 2 and 3. Is that fine? Okay. This is straightforward because this is directly connected to the input and I know what the input numbers are. Now if I look at the highlighted node in the second layer or any subsequent deep layer, if I have the node numbered 2, again using the same semantics that it should only see the inputs which are less than or equal to 2, how do I ensure that? It should be connected to nodes in the previous layer which are less than or equal to 2, right? So it should only be connected to those nodes which have seen less than or equal to 2 inputs, which means those nodes which have a number less than or equal to 2. Does that make sense? Everyone gets this? Please raise your hands if you get this. So now this guy will only be connected to all those nodes which are numbered 1 to 2. So I've got rid of many connections and only kept those connections which are relevant. And now I can take this all the way up to the output layer. If I have a node number 3 in the output layer, which are the nodes that it will be connected to in the previous layer? Anything less than equal to 2. I think I'm using less than equal to and less than interchangeably, but I think that's clear from the context, right? So this is only connected to these nodes. These nodes in turn are only connected to certain nodes in the input, and those nodes are only connected to these 2 inputs, right? So I have transitively made sure that the third output node only sees the relevant input nodes. Okay, fine. This is again very similar to what I am dropping out certain connections. Very similar to drop out. Okay, what's the loss function going to be? What's the loss function going to be? Sum of cross entropies. What's the learning algorithm? Backpropagation only through the relevant paths. And this thing which I have shown here, it's just not for the sake of it, I'll explain what that mask is now, right? So in this case, this was the original fully connected W matrix. So I'll always have the full W matrix. Only thing I'm going to do is I'm going to use an appropriate mask to it to do the relevant computations. And the way I had numbered these nodes, it turns out that if I apply the following mask to the weight matrix, right, then it will ensure that only the relevant nodes participate in the computation, right? So I think this is very straightforward. So look at the first column. It's all ones. I don't want to mask out any of these weights. Why? Because everything in this second layer is connected to the first node, right? Now let's look at similarly for this guy, right? Everything in this layer is going to be connected to the third node. So that column has all ones. I don't need to mask out anything from there. Now let's look at this layer. So only the third node here, no, only these 2 nodes, right, third and second, are supposed to be connected to this node. So I have 2 ones over there. Is that fine? So that's exactly what these masks are showing. We'll apply these masks to the weight vector or weight matrix. It's going to be a Hadamard product which reduces some entries to 0 and retains the others. And this makes sure that in your computation at the next layer, only the relevant inputs are participating. Is everyone okay with this? Do I need to explain this masking again? The objective function is again going to be a sum of the cross entropies. The network will be again trained using backpropagation, and the backpropagation will only happen through relevant nodes. Yeah, so you do this random number assignment once, right? After that, the masking is hard-coded. Manually do means you have to just define this mask matrix, right? Yeah, but this is just an element-wise multiplication, right? This is not an expensive operation. No. So you don't need to randomly assign numbers to the nodes. You can directly randomly create the mask matrix. Instead of going from the numbers to the mask matrix, just define the mask matrix, right? In fact, this explanation is done in a way so that you understand it, but in practice, you'll just have the mask matrix. That tells you what numbers the nodes have. Yes, so you'll have all images of size 32 cross 32 or something, right? If you don't have images of size 32 cross 32, just resize them to 32 cross 32, right? So that's always assumed. All the inputs will have the same size. Okay, because these are random variables, so the number of random variables has to be fixed. Okay, anything else? So again, this model is not really designed for abstraction, but can you do generation using this model? How will you do generation using this model? We just did NADE like 5 minutes back or 10 minutes back. How will you do generation? Same thing. What will you do? First sample a value for x1, feed that in, compute a value for p of x2 given x1, and you can do that because it only depends on x1, only those paths will be activated, and you'll get a p of x2 given x1. Now you'll sample a value of x2 from this Bernoulli distribution, feed that in, compute a value for x3. You can do that because only those paths will be activated. Okay. Again feed that. Again 1 pixel at a time, you can do the generation. Is that fine? Everyone okay with this? Okay. So these are two fundamental or rather almost foundational autoregressive models that you need to know. The ideas that you need to pick from here are the following. One is you can work with the explicit factorization where you have these n factors without any independence assumptions. You can then use a neural network to parameterize this distribution so that you don't have an exponential number of parameters. The idea of masking is central to both these approaches because masking ensures that only the relevant inputs contribute to particular outputs, because your outputs have a certain ordering xi given x1 to xi minus 1, and this masking ensures that. At the end of the day, both of these are just neural networks, so you can use backpropagation, and the loss function is just going to be a sum of the cross entropies, and backpropagation only needs to happen over the relevant paths. This is not something new. We have already seen this in dropouts. Even in dropouts, we ensure that the backpropagation only happens through relevant paths, right? It's the same. Now, these are not state of the art in the sense that today when you hear about autoregressive models, what people talk about is pixel RNNs and pixel CNNs. So that's what I want to do next. By next, I mean today itself. I'll just continue. So I think it's already 12 o'clock. So people who have to leave can leave. The others can stay back. I need roughly half an hour more to finish off pixel RNNs. It's again an autoregressive model. I'll make sure that this recording is up today itself so that you can immediately go and see it. So people who want to leave can leave. I'll just finish off pixel RNNs also now. If you have lectures, you can just go. I'll just take a break for 5 minutes and then finish. Right? It isn't. But what you did is you started with an autoencoder which has n inputs and n outputs and tweaked that into a density estimator. I was going to say destiny estimator, but okay. Right? So that's why. I mean, it's just wordplay in my opinion, but yeah, it's not really an autoencoder. I mean, the motivation came that, okay, you have this, an autoencoder which has n inputs, n outputs, and here again you have a setup where you need n inputs and n outputs, so why not just take that and tweak it a bit. Okay, so what you're going to do now is something known as pixel RNNs, which is actually the basis of a lot of cool generative models, including wavenets. How many of you have heard of wavenets? This is Google's music generation stuff, right? You can go and look it up. It generates pretty nice music. So the basis for that is pixel RNNs, and that's what we are going to look at it. It's again an autoregressive model. The moment I say autoregressive model, what does it mean? The factorization that you're going to use is going to be the default chain rule. There are not going to be any assumptions in that. And the entire quest in proposing or building an autoregressive model is to come up with ideas such that xi only depends on x1 to xi minus 1, right? The entire engineering goes into that, and that's what we saw in NADE as well as MADE. We defined the equations or the masks in a way such that xi only depends on x1 to xi minus 1. So that's the main part. Otherwise, the setup is clear. You're given n inputs, you're given n outputs. The outputs are actually going to predict probability distributions, right? And even the sampling part remains the same. You are going to sample 1 pixel at a time. So all that remains same. It's the only way they differ in it is how do you go from this input to the output while ensuring your criteria that you should only look at the relevant inputs, right? That's the only thing which changes, okay? So now with that in mind, we're going to start, since this is pixel RNNs, we're going to start with RNNs, okay, and then kind of build towards what pixel RNNs is and start with certain characteristics of RNN. So if you have a regular RNN, right, so let me just see how to draw that. So you have this input X, okay, this is rather Xi, right, so you have X1, X2, and so on. X1, X2, and so on, right? Now, what you have is first an S1 and then an S2, right? And what kind of connection do you have from X1 to S1? Sparse or fully connected? So S1 has some D nodes. Does every node in S1 depend on every input in X1? It's a fully connected layer, right? That's what this is, right? And what about the connection from S1 to S2? It's fully connected. Every node in S1 contributes to every node in S2, right? And that's obvious because you have this matrix multiplications, right? Now, a cryptic hint, but if I want the input or if I want the output, right, SI, to depend only on certain inputs, not all of them. That means instead of a fully connected network, I want a sparse connectivity. What do we know which helps us in sparse connectivity? Asking, okay, if I had not done today's lecture, sparse connectivity. What kind of an operation allows a sparse connectivity? I'll just draw something in the meantime while you're answering. What operation is this? Is my drawing so bad? What kind of an operation allows us this sparse connectivity? Convolutional neural networks have sparse connections, right? So how do you write a convolution operation? Instead of product, how do you write it? Right? What does this mean? That you use some kind of a filter, it will go over only some portions of Xi and compute a new value, right? So it would mean that I have this Xi, okay? Now right now what I have is a U, which is like a fully connected weight matrix. So all my outputs depend on my inputs. Instead of this, if I use a convolution operation, what would happen? I'll have my inputs. I'll apply a convolution filter. Every filter, every pass of the filter or every stride of the filter is going to give me, forgotten everything about convolution. It is going to give me 1 pixel in the output, right? So I'm going to get a similar sized output, except that every guy here only depends on certain inputs, right? Why am I ranting about this certain inputs depending on certain inputs? Because what are we studying? Autoregressive models. What do we want there? That the outputs should depend only on certain inputs. All I'm telling you is that convolution operation gives you one way of making sure that your output depends only on certain inputs. Okay? Is that fine? Is that okay? Fine. So that's what a standard neural network does, and standard recurrent neural network does. And of course, an LSTM is much more complicated than that. But if you look at all, you remember all these four equations that you have for LSTM, they're all similar, right? You have a W, you have a U and a B, you have HT minus 1, XT and B naught, right? What matters is all these are fully connected operations. And I'm not okay with fully connected operations because that means every output depends on every input, okay? So that's, I'm not saying this is a problem with RNNs, I'm just saying that this is what standard RNNs and LSTMs do. Every output depends on every input. Every gate depends on every input. Okay? Is that fine? Okay. So remember now, let's look at this gate again. So say this is your Ft, and your Ft is going to multiply by St minus 1. Okay? So this is an element-wise product. So this is an element-wise product. But what I'm trying to tell you is that every element here depends on all the previous guys, right? Because it's a fully connected layer. Do you get that? So you can think of these as, if the dimension is D, you have these D LSTM cells, okay? But all of these cells are fully connected to each other's output. The gate for the Dth cell depends on everything that happened in the previous timestamp, okay? So all of these are fully connected layers. Is that okay? Everyone fine with this? Okay. So this is just reiterating about LSTMs, okay? Now coming back to our goal is that given an input, and now I'm going to talk only in terms of images. So given an input, which is an image, so which would be n cross m, or I'm going to assume n cross n for this discussion, right? So this is an n cross n input given to it. Our job is to compute n square probability distributions. So you have this p of x1, p of x2 given x1, all the way up to p of xn square given x1 to xn square minus 1. Is that fine? That's what our job is in the case of an autoregressive model. What's the other thing that we need to ensure? I have highlighted a certain node. What do I need to ensure? It only depends on previous inputs. And here we are going to define previous as the following. Right? You see the bottom figure? So here there is 1 to n square. Here again there is 1 to n square. There is a 1-to-1 mapping between them. So when I am going to compute the ith unit, it should only depend on 1 to I minus 1. Is that okay? That's what I want to ensure. Fine? And what pixel RNNs do is they use something known as spatial LSTM. Okay? We'll see what a spatial LSTM is. You'll have multiple of these layers stacked upon one another. So this is actually a spatial LSTM. I'll define what it is. But you have 12 such layers stacked on top of each other, and this is your final output layer. From here you are going to predict these p of xi given x1 to I minus 1. Is that okay? That means this guy should see only everything which appears before this, and I should ensure that all of these in turn are only dependent on these blue guys. Is that fine? So I have to define my LSTM operation in a way that right from the input layer onwards, I have this 1-to-1 correspondence between these layers, so that I know that when I'm looking at the ith guy here, it only takes input from 1 to I minus 1 guys, right? So in particular, this ith guy will only depend on these 1 to I minus 1 guys, and I have to make sure that in turn they also depend only on the corresponding inputs, right? If I can ensure this for every pair of layers all the way up to the input, then I have ensured that the output has only seen the relevant inputs. Is the setup clear to you? How many of you are fine with this? Please raise your hands. Okay. Now let's look at one such pair of layers. Okay, fine. So I'm looking at, I have computed this layer already, and now I'm trying to compute this layer. Okay. I want to make sure that this red node in this layer only depends on the relevant inputs from the previous layer. Okay? And all of these nodes that you see, they are actually LSTM cells. They are single dimension LSTM cells. Okay? That means all of them have their forget gates, all of them have their input gates, all of them have their output gates, all of them take an input, and all of them take a given output. Okay? And all of them also depend on the previous hidden state. Now what I need to tell you is, how do I define the input and how do I define the previous hidden state so that everything is kosher? And what do I mean by everything is kosher? That every guy here sees only the relevant inputs. Is that okay? Fine. So now let's look at this LSTM cell. So what I'm going to ensure is that in a normal LSTM cell, all these inputs, all these n square pixels that I have shown here would have contributed to this one cell, right? That's exactly the case which I was trying to make on the previous slide, that each of this is fully connected. So even if I look at the red guy in the top layer, it would have been fully connected to everything from the previous layer. Do we want that? No. We just want to work within this boundary. Okay, we just want to work within this boundary. Okay? So the way you define this spatial LSTM is that I'll first apply a convolution operation for every row on the previous layer. Okay? Is that fine? So let's see this. So I have this previous layer. I'm going to apply a row-wise convolution operation or a one-dimensional convolution operation. Okay, that means I'm going to take a filter and slide it across the row. What is the output that I'm going to get? Another row, right? And every pixel in that row would depend only on the previous pixels. Is that fine? Everyone okay with that? So if I take this input which I had and I apply a convolution on that, then I'm making sure that in the output of the convolution, every guy only depends on the previous inputs. Is that fine? Everyone okay with that? Okay. So now from this, you can imagine I have taken one more. From here, I have computed an intermediate layer. From this layer, I have computed an intermediate layer where every pixel now depends on the previous convoluted pixel. Okay. It only depends on the previous guys. It does not depend on any guy. Fine? Okay. Okay. So now let's imagine this is the output of that convolution layer where every guy only depends on the previous input. Now I want to compute the next layer from there and I want to use an LSTM. Okay. If I want to use an LSTM, I need to define two things. I need to define the input and I need to define the connections from the previous state. These are the two things that I need to define. So now suppose I am at this point. The input to the LSTM is only going to be this pixel and the previous pixel. Okay, is that fine? What's the problem with this? What did I want the pixels to depend on? All the previous inputs. What have I done now? Only one previous one. So I have to give a justification for that. Okay, but I'll come back to that. For now, is it okay? Okay. Now the other thing which I'm going to do is that for this guy, you can think of all of these as ht minus 1. These are the things which have already been computed so far, right? So now one, and the standard LSTM, what I would have done is this guy would have been connected to all of them, right? So I'm not going to do that. I'm again going to define a convolution operation which ensures that this guy only depends on this row. It only depends on the 3 pixels above it. You can imagine a convolution operation which does that. It just takes the previous row, applies a 3x1 mask on it, 3x1 convolution on that. Okay, so you'll get a new row. Every guy here depends on 3 guys around here, right? And now this guy can feed to this input. Is that okay? It's okay if you don't understand the details of the implementation, but can you imagine that I'm only making it dependent on the previous 3 pixels? Now these 3 pixels in turn depended on 3 pixels from the previous layer. Is that fine? Okay. And what was the input to this guy? Is that fine? What was the input to this guy? This. And so on, right? So in turn, because of this transitive thing, this pixel has now become dependent on all the previous pixels that it had. Is that clear? Do you get this? Please raise your hands if you do. Not many people get this. So what I was saying is that this layer has been computed. Okay, fine. And now I'm interested in computing this value. I need to ensure that it depends only on the previous guys. That's what my goal is. Okay, is the goal clear to everyone? Okay. Now each of these things, each of these pixels here is actually an LSTM. That means it has an input gate, it has an output gate, it has a forget gate. It takes input from the previous layer, that's the X. And it also has recurrent connections from HT-1. Okay. Now what I'm trying to define is X and H. So forget everything that we did so far, I'll just start fresh. I need to define X and H. So what I'm saying is that the X is just going to be this pixel and the previous pixel. Okay. Is that straightforward? I'm just going to make it, instead of having a fully connected representation, so in the fully connected case, all of these pixels would have contributed to this one pixel. But I don't want that, because I want to make sure that every output only depends on the relevant inputs. Okay. So to ensure that, what I wanted is that it should have dependent on all of these. Okay. As of now, what I'm telling you is that I will only make it dependent on this pixel and the previous pixel. That's what I'm telling you as of now. Okay. So that's, I have defined what xt looks like. Now I need to define what ht-1 looks like. Okay. So my definition for ht-1 is that it will only depend on the 3 pixels above it. Is that fine? Again, it could have been a fully connected connection, but I'm just going to make it dependent on the 3 pixels before it. Is that okay? But this pixel in turn was dependent on 3 pixels above it. And this was dependent on these 3 pixels, and this was dependent on these 3 pixels. Okay? Now in turn, this pixel would have taken input from here, right? Is that okay? So transitively now, this, since this pixel, the one which I'm shading right now, contributes to the central pixel, transitively this pixel also contributes to the central pixel. Is that fine? The same thing I can argue about all these pixels, which I'm shading now. All of them transitively contribute to the pixel of interest. Is that okay? Everyone gets this? Okay. So now in some way I've made sure that xi depends on everything from x1 to xi-1. Is that fine? Okay. So that's exactly how these LSTM operations are defined. So remember, in the original LSTM equations you had this matrix multiplication. Now we have replaced all of them by convolution operations, and the convolution operation ensures that there is this sparse connectivity where only the relevant pixels contribute to the next pixel. Is that okay? So we have taken the LSTM equations and just converted them to replace the fully connected operations to convolution operations, right? So that's exactly what a pixel RNN does. It has these, it has this deep layer of spatial LSTMs. All these LSTMs have a unique connection. They only depend on the previous guy, and transitively that I ensure that this particular pixel only depends on the relevant inputs that it should depend on, right? And now instead of having a normal feed-forward neural network, I have these LSTM neural networks because they also take inputs from the previous state, so that there's a recurrent connection between these. The only thing is that instead of having a fully connected recurrent connection, you have a convolution-driven fully connected, convolution-driven hidden connection or a recurrent connection, right? So that's what pixel RNNs do at a very high level. So now we can go back and read the paper and try to understand it. So the paper actually has many more details beyond this basic framework. What I wanted to explain to you is that starting from an input and given this goal that your output is conditional probability distributions such that each value in the output depends only on certain inputs, how do you ensure that? So that's the intuition which I've tried to give you. Now the paper has several more details. They use something known as row LSTM, something known as diagonal LSTM, then some skip connections and so on. So now with this intuition, if you try to understand the paper, you should be able to understand it better. So you can go back and take a look at it, right? So I'll just end here.